Hello, can you hear me? Please let me know in the live chat if you can hear me. Hello? Hi, everyone. Awesome, awesome. Thanks, Ashutosh. Thanks, Ashutosh. Good morning, Ashutosh. Yeah. Everyone in the chat, everyone who's here. Good morning, everyone. So let's get started without any delay. So hello, everyone. I'm Sai Avinash, and in this lecture, I'll be teaching in this lecture series. This is a new lecture series. It's about dynamic programming. And it's going to start with really easy problems, and I'm going to take it up further, up to medium problems, medium to hard problems. And I'll be following the structure of the Atcoder DP contest, which is laid out in a really nice way, so that you can understand the concepts, and I'll implement them in front of you as well. After doing this course, after watching this lecture series, you would have a decent grasp of dynamic programming, and like in Codeforces, for example, in Codeforces, you'd be able to solve up to C, div to C problems in dynamic DP and so on if you follow this lecture series carefully. So let's get started without any delay. Hi, Jack. Hi, Millen. Yes, this is super beginner friendly. You'll see yourself like how beginner friendly this is. All right. So again, I'm Sai Avinash. I'm an SREC at Google Dublin. I'm All India rank 4 in CodeChef. I'm maximum rating as international master at Codeforces. I've previously been the master. I'm currently master. I previously interned at Uber, and I'm also ranked on finalist. The subjects that I take are discrete maths. I've taken maths in my last lecture series. Dynamic programming, which is going on now. Graphs, which will go on later. So use the code SciLife to get 10% off on the Unacademy Pro subscription. So here we have a career as a software developer subscription. It has interesting shows covering a variety of subject topics. It shows around live problem solving, and it's just $9.99 per year. So people who are in the software and technology domain who want to enable lifelong learning, this course is for you. And if you think you want to keep learning CS core fundamentals, this is the right course for you. So use the code SciLife to get a 10% off on the Unacademy Pro subscription. So every Friday night at 10 p.m. we have Raj Vikramaditya, and this is taking a session on college projects. So he's going to review college projects, and he's going to tell what has scope for improvement, what's missing from the college projects, or what's being done well in the college projects, and so on. And this is going to be a part of the Unacademy's career as a software developer subscription. So Varun Manchanda is asking, please start with the recursive approach. Yes, that's where I'm going to start with, and then I'll go to the iterative approach. Yes. Govind Majage is asking if I'm going to solve all problems of the Atcoder DP series. I'll leave a few problems in the end because they're not so easy. I can explain them, but it won't be beginner friendly. I'll decide that later, actually, So you subscribe to this Telegram channel and to get live updates on when classes are going to happen. So that you don't miss out on any. So if you think this content is going to be useful to you, do like, and if you haven't shared it already, share it with your friends. DP is a really important topic, and as you might already know, I don't have to explain it. And that's it. If you haven't subscribed already, do subscribe. So let's start with the first problem. Frogs 1. So, what's the problem here? All right, let's look at the problem here. Ashutosh, the number of lectures would be equal to the number of problems that I'm going to cover. Each lecture has a single problem. All right. So there are n stones numbered 1 to n. For each I, the height of the ith stone is hi. There is a frog who's initially at stone 1. He will repeat the following action some number of times. So he'll do this a number of times to reach the ending stone, which is stone n. So the frog is currently at stone I. It either jumps to I plus 1 or I plus 2. So the frog is at 3. It jumps at either 4 or 5. and so on. Now, the cost of jumping from one stone to another stone, like if he jumps from 3 to 5, the cost is hi minus hj, absolute of hi minus hj. Meaning, if the height of the stone I is 5 and height of the stone 3 is 5 and height of the stone 5 is like 10. So the cost will be 5 minus 10, absolute of 5 minus 10, which is 5, absolute of minus 5. Like you don't take the without the sign, absolute value, right? So what is the minimum total cost incurred before the frog reaches stone n? Look at the constraints. Constraints are n is up to 10 power 5, hi is up to 10 power 4, heights are up to 10 power 4. Let's look at the example. If n is equal to 4, there are 4 stones, 10, 30, 40, heights of 10, 30, 40 and 20. You want to reach from 10 to 20 as quick as possible. So one way to do that would be to jump from 1 to 4. The cost would be absolute of 10 minus 30, which is 20. 10 to 30, and then 30 we can directly jump to 20. We don't need to go through 40 because that's going to be more costly. We want to calculate the minimum cost. Got this? I'll show it to you with an example. Yeah. So let's look at an example. So if we have n equals 4, say the numbers are 4, 7, 6, 3. How would you go to 4, 6, 4, 7, 6, 3? The heights are this, h1, h2, h3, h4. So if you want the frog is here, frog is currently here. It wants to go till here somehow, but it can't jump directly. So it needs to follow a few steps to jump. And by following these few steps, we want to minimize the total cost. And the cost from going from h1 to say h3 is just 4, absolute of 4 minus 6, which is 2. 4 minus 6 plus 6 to 3. 6 minus 3 is equal to 5. Or we could also go from 4 to 7 and then 7 to 3. Or we can go from 4 to 7 and 7 to 6 and 6 to 3. So let's check 4 to 7 and 7 to 3. 4 to 7 is 4 minus 7 plus 7 minus 3 is equal to 3 plus 4, 7. This is too costly. Why do we take a costly route when we have an easier route here, smaller route here? Let's check from 4 to 7 and 7 to 6, then 7 to 3, 6 to 3. 4 to 7 is 3, 7 to 6 is 1, and 6 to 3 is 3. This is plus 3, plus 1, plus 3. That's totally 7, which is costly again. So this is our best solution. So we should print the number 5. We should print the minimum cost. Got it? Any doubts on this problem so far? Any doubts on the question itself so far? Any doubts? If you have any doubts, please let me know in the live chat. And if you've understood it, please let me know that, yes, sir, I've understood. Yes, I've understood it. It's clear. Please let me know in the live chat so I can continue to proceed to the, yeah. Is there anything you want me to re-explain? Awesome, awesome. All right. So, how do you solve this problem? How do you solve this problem? So, look at like how do we solve this problem? So, what are we doing when we want to jump to step like the last stone? Let's look at the last stone. Let's look at the last stone. Let's look at the last stone. Now, if we want to jump here, we either jump from the stone n-1 or stone n-2, right? Let's say the cost here is, cost to reach n-2 is A, cost to reach n-1 is B. And say from n-2 to n is something, and n-1 to n is something. Yes, we can do easily recursion. Yes, check all possible steps. Exactly. So basically, answer of n is same as answer of n is equal to same as answer of n-1. If you go from n-1 plus cost from n-1 to n, that is same as, how much is that? Cost answer of n-1 plus h n minus h n minus 1. because this is the cost to reach from n minus 1 to n. It's either this max of or answer of n minus 2 plus hn minus 2. Man, okay, sorry. Isn't it? That's it. That's our recursive. We just need to so in dynamic programming, we just need to make the recursive formula and things will all fall into place by itself. Let's look at what we did again with an example. What did we write the recursive formula as? Answer of n, min of answer of n minus 1 plus absolute of, just write the cost, hn minus 1, and answer of n minus 2, you can jump from n minus 2 as well, right? Plus hn minus 2. That's it. We are done. But how do is this clear? Like, you either jump from hn minus 1, then say we know the answer of n minus 1, we get answer of n directly. If you know the answer of n minus 2, we get the answer of n directly from these two answers. Like, if you know answer of n minus 1 and n minus 2, we get answer of n directly by just taking the minimum of both of these equations. Yes, min of both of these equations. Oh, I'm sorry if I told max previously. It's minimum of these two equations. For example, let's take an example. For example, let's look at the example in the question itself. 10, 30, 40, 20. 10, 30, 40, 20. Answer of 1 is just 0 because you're just there and that's it. Answer of 1 is 0. Answer of 2. Answer of 2 is answer of 1 plus absolute of 30 minus 20. Answer of this is 20. Answer of 3, like answer of 4 till 40, like the stone of height 40 is 20 plus 40 minus 10. Minimum of 20 40 plus 40 minus 10 and or 40 minus 0, 0 plus 40 minus 0. In this case, you're getting both of them same. So this is 30. We write the answer 30 here. 30. Let's look at the answer for 20. It's either answer of n minus 1, which is 30. 30 plus absolute of 40 minus 20, or 20. It can jump from here or it can jump from here. 20 plus absolute of 30 minus 20, which is equal to 50. This is equal to 30. And minimum of these two answers is 30. That's what we're doing here. Where is this here? That's the answer. Answer is 30. That's it. It's very straightforward. For a small n or for a big n like this. We can do it for this also if you want. You can do it for this as well. Alright? Awesome. Is this recurrence clear for everybody? Is this recurrence clear for everyone? Any doubts? Do you want me to re-explain any part of this? First, I'll do the recursive approach and then I'll do the iterative approach. Any doubts so far? I'm looking at the live chat. So this is a pretty straightforward problem. It's a beginner friendly problem, and even if you just know basic programming, you can just like go ahead with this. Like, all right. Any doubts with this? Some of you might have got it without even me telling it. So that's good stuff. All right. Let's just code this up quickly in a recursive approach. All right. So one second. All right. So what are we given? We're given integer n. Let's look at what we're given here. Integer n and then n numbers, h1, h2, so on till n. Gone. Got it. We take the input n. vector int h of n for int I equals 0, I less than n, I plus plus c in h of I. Now, let's declare this globally for now. H dot vector int h. All right. Let's go ahead and code this. See out. What are we going to do? We're going to do solve of n. And I'll fill the solve. No worries. Like, I'll just fill it now. Int solve int n. If n equals 0, if n, the base case, if n equals 1, return absolute of h of 1 minus h of 0. If n equals 0, return 0. These are the two base cases, right? These are the two base cases. Awesome. Now, how do you solve for bigger? Return minimum of solve of n minus 1. So let's write the two answers. Int first jump equals solve of n minus 1. We have the jump from n minus 1 plus absolute of h of n minus h of n minus 1. In second jump, same thing, but n minus 2. We replace minus 1 with minus 2. Simple. Return min of first jump, second jump. That's it. That's our answer. That's our answer. That is simply our answer. Got it? Awesome. Oh, sorry. Awesome. Just forgot a semicolon here. Awesome. This is clear. Awesome. But what is the problem with this? Can someone tell me what the problem with this? This is n is up to 10 to the power 5. What is the problem with this? What is the problem with this solution? N is up to 10 power 5. Can someone tell me what the complexity of the solution is? Someone got close to the complexity. Someone said it's 2 power n. You're close, but it's not exactly 2 power n. Okay. It's exponential. Yes, exactly. It's gonna TLE. Exactly. So why is it gonna TLE? What are we doing here? For answer of n, we're computing answer of n, we're computing answer of n minus 1, computing answer of n minus 2 as well. It's not 2 to the power n. It's not 2 power n. It's not 2 power n. It is not 2 power n. No. I'll tell you what it is. So let's look at how many steps are going to happen. So for computing n, you're computing both n minus 1 and n minus 2. So the complexity for n, let's call that C of n, is equal to C of n. Number of steps to take to compute n is, let's call it C of n. It's equal to the number of steps to compute n minus 1 plus number of steps to compute n minus 2. Correct? C of n minus 1 plus C of n minus 2. And similarly, C of n minus 1 is equal to C of n minus 2 plus C of n minus 3, so on. Isn't this the recurrence of Fibonacci equation? Isn't it? It is. Fibonacci equation is Fn equals Fn minus 1 plus Fn minus 2, right? So the number of steps to compute n, the answer for n, it's going to be Fibonacci of n. It's going to take Fibonacci of n times, of n steps, for example. Is that clear? And we know that Fibonacci is about, it grows exponentially, right? It grows exponentially. Some of you are close. It's not 2 power 10 power 5, but it's Fibonacci of n. Fibonacci of n. And that as we know, it grows like exponentially. Yeah. And if you want the rough growth, it's about 1.618 per n plus something 1 by 1.618 per n, but that's not required. This is the ratio it grows with. Some of you told it's 2 per n, close enough. It's okay. But it's still exponential and it's not feasible as we saw it, right? So how do we do this quickly? How do you do this quickly? So, any doubts with this? One second. Just give me a minute. Yep. Any doubts with this approach? Hi, Pawan. Yes, Jack Walker has it. Yeah, memorize it. Yeah. How do we do it quickly? First of all, we can memorize it. Okay, my handwriting sucks. Okay. We can, once you compute n minus 1, we don't need to compute n minus 2 and so on. We don't need to like recompute n minus 1 again, right? You don't need to recompute n minus 1 and so on, isn't it? So that makes our problem easier. For example, like we had 3, 5, 7, 2, and n equals 4, for example. We have the answer for 3, it's 0, answer for 5 is 2. Answer of 7 is answer of 5. From here we go here, or from here we go here, which is 2 plus absolute of 7 minus 5, which is 4. Minimum of 4, comma 7 minus 3, which is 4. In both cases, you're getting 4. All right. Now for the answer of 2, we know the answer of 5, which is answer of 7, which is 4. It's min of 4 plus absolute of 7 minus 2, and 2 plus absolute of 5 minus 2. See, when we wrote 4 here, answer of 7, answer of like 3 here, answer till here, we are not recomputing it again because we already know the answer. Why do we need to recompute it, right? You don't need to recompute it. Like if it's already computed, let's be lazy here. All right. So what are you doing here? We store these answers. Since we are not storing them anywhere, like we are recomputing it each and every time, instead of storing it, let's store it and then look at the complexity. Let's store it in an answer called DP, and the size of the DP is going to be DP dot n as well. Let's initialize all of them with -1 first of all. Let's initialize all of them with -1 and then deal with it. Now, what we're going to do instead here is, instead of recomputing it each and every time, we recompute it exactly once, and every other time, if it's recomputed already, we don't recompute it again. If it's computed already somewhere before, we don't compute it again. That's what you're going to do. All right. So dp of n equals dp of n. dp of n. I can write dp of 0. I'm just writing dp of n equals 0, returning dp of n everywhere. dp of n equals, it's very simple. Introducing, once you know the recursive formula, introducing dp is like very straightforward. It's very trivial. You just store the answer, and then see, right now we didn't change anything in the logic. We just stored it in dp of n, we return dp of n. All right. We stored this in dp of n, we return dp of n. We stored this in dp of n, and we return dp of n. Now we know that dp is never going to be -1 here if it's already computed. If the answer for n is already computed, initially we initialized all the dp's with -1, all the answers with -1. Now if some answer is already computed, we know that we know that the answers are going to be positive, like since 0 or above, right? So once you compute dp of n, it's not going to be -1. So if the answer is computed, how do we check if the answer is computed? If dp of n is greater than or equal to, it's not equal to -1, then we already return the answer. Very straightforward. All right. Is this clear? Is this clear, everyone? Any doubts with this? So what do I do here? Now, the complexity of this, like just just by introducing introducing this technique, just by introducing this, this is called, now we are just memorizing the answers, like memoizing the answers. O of 1.6 power n to O of n. Now we just by introducing this tiny trick, we came from exponential to linear, and that's what DP is all about. Like, it's not all about, like, coming up with a recursive relation is usually the trickiest part. It is almost all, it's a lot of times it's the trickiest part, and this is just like storing the answers, being lazy about it, and now you're very quick. Yes. So if you look at this here, we're going to compute it only for 1n. So you asks me, to be good at DP, should one be good at PNC? Not necessary, but it helps a lot of times to be good at combinatorics here. So what are we doing here? For a given n, we are computing it exactly once. So for some, say for DP of 3, we do solve of 3 here. We come here and we compute solve of 3. Now again, if someone calls for solve of 3, we don't recompute this, because this check fails here itself. Like, once we compute 3, DP of n will no longer be -1. It'll be some actual value. It'll be the answer of n. And then we return this directly. Is that clear? Is this clear, everyone? Any doubts with this? Any doubts with the solution? Any doubts? Looking at the live chat. No doubts? Awesome, awesome. So this is the recursive approach, and the iterative approach isn't like is pretty straightforward too. I'll do that for you guys here. So if you notice the complexity of this, it's just, since we're computing for each number in O of 1, like we're computing for each number exactly once. I'll just look at how the structure looks like. Okay, I'll just show you how the structure looks like for computer. Like for DP, it's important, like, to know that the structure looks like a directed acyclic graph. It's okay if you don't know what a graph is, but it looks something like this. So for computing answer of, say, 6, we wanted answer of 6 calls answer of 5 and answer of 4. Answer of 5 calls answer of 4, answer of 4 and answer of 3. Answer of 4 calls answer of 3 and answer of 2. And answer of 3 calls answer of 2 and answer of 1. Answer of 2 calls answer of 1 and answer of 0. Answer of 1 calls answer of 0. If you look at the structure, there are no cycles in the structure. So if you compute answer of 0, we get answer of 1. If you compute answer of 1 and answer of 0, we get answer of 2. So there is an underlying, if you look at it from above, like what function is calling what with which parameters, it's going to look like a directed acyclic graph, and it has to be. Like, you can't form your equation in such a way that answer of 3 again calls answer of 6. No. In general, this is in general for DP. There can't be a cycle. If answer of 6 calls answer of 5, then answer of 5 calls answer of 3, and answer of 3 again calls answer of 6, then 5, then 3. That's going to be a loop, and you won't have an answer there. You need to either break at some point, or you shouldn't have this structure. Got it? This structure is nice, and it's called a directed acyclic graph. You can see that there are directed, like answer of 6 is calling answer of 5, answer of 5 is calling. There's going to be a structure here if you look at the structure. All right, awesome. And if you look at it closely, once you ask for answer of 6, answer of 5, you call answer of 5 and answer of 4. And for answer of 4, you need answer of 4 and answer of 3. For answer of 5, you need answer of 4 and answer of 3 and so on. And again, when you like first answer of 6 calls answer of 5, and then answer of 5 calls answer of 4 and answer of 3 and so on. So once answer of 5 computes answer of 4, when answer of 6 calls for answer of 4 again, it doesn't recompute the whole thing. It already returns the already computed answer. It returns the already computed answer, which is stored in DP, because DP is not -1 anymore. Alright? This is DAG structure clear? I'll explain the DAG structure. I'll keep explaining bringing up the DAG structure multiple times. Okay? Is this clear so far? No, Biram says DAG is basically a tree. Then no, it's not a tree. Tree is where this is a tree. DAG, it's a totally different concept. A tree doesn't have to be directed or not. For example, this is not a tree. This is not a tree. There are no directed cycles here. There are cycles here, but they're not directed. Like that, they're different concepts. I'll come to that later when I teach graphs. Okay. Awesome. Awesome. So let's look at the iterative approach as well. Iterative approach. We'll just write the same equation. Iterative approach. So dp of, let's write the base case here. dp of 0 equals 0. dp of 1 equals h absolute of h of 1 minus h of 0. Why I'm teaching the iterative approaches? The recursive approach uses stack space. If you look at it here, when you call answer of 6 calls answer of 5, answer of 4, then answer of 3. It's all stored up in a stack. The function calls is stored up in a stack, and that uses some space, right? Like when you're at answer of 1, it needs to return the answer to answer of 2 again back. So it needs to know where to return. So there's this a linked list kind of a structure where one function needs to know where to go back, and that uses some stack space. So yeah, so there's that. For int I equals 2, I less than, that's why sometimes iterative can be even faster. dp of I, again we'll just write exactly what we wrote here. Int first jump equals dp of I minus 1 plus absolute of h of I minus h of I minus 2. Second jump is I minus 2 plus I minus. That's it. The second jump is dp of I minus 2 plus absolute of. Now what we do, we take minimum of both of them. I equals minimum of first jump, second jump. CR dp of n minus 1, since we did the 0 indexing. Yes, sometimes stack overflow might occur, like depending on the stack size of the computation you're submitting it to. All right. Is this clear? So I just computed everything up till I, and then I know the answer for I plus 1. This is a super easy problem. This is like one of the easiest problems you can get in dynamic programming. Like it can't get easier. And this is where we'll build up your concepts from. All right. Is this clear? Any doubts so far? If you look at this, I'm just creating an array of size n, new array of size n. Additional complexity, you can call it O of n. This is the already given input. This is O of n. Now, if you want to do it a bit quicker, like if you want to use just O of 1 extra memory, you can do that too. How would you do that? This is O of n extra memory and O of n time complexity. You can do it quickly, even quicker as well. I'll show you how. So we can do it even quicker. Answer of n is equal to answer of, for answer of n we need answer of n minus 1 and answer of n minus 2. We don't need everything before, right? That's it. That's what we're going to use. We don't need this. We don't need this. Let's eliminate this and I'll show you what we're going to do. Int previous to previous is equal to 0. Previous equals this. Now, first jump is equal to previous and second jump is equal to previous. That's it. That's it. First jump comes second jump. Now we need to update what first jump is. So previous contains just dp I minus 1. Previous to previous contains dp of I minus 2. And I keep updating it as I go on. Alright? I keep updating it as I go on. Now, previous to previous will become previous. And previous will become dp of I. Now once next I go for I plus 1, my previous will be dp of I. And for I plus 1, previous to previous will be dp of I minus 1. And that's what I'm doing. If you look, and here I can just write previous in the end. Because when I come towards the end, if I equals n minus 1, my previous will be, and the answer would be stored in my previous, right? We can use just like, this is just over fun extra space. Well, it's not really needed, but I'm just telling that to you, like, sometimes you need techniques to, reduce your memory. So we just stored what's necessary. Once you're at I equals say 50 or something, we don't need everything up to 48. We just need 48 and 49 to compute what the answer for 50, right? So any doubts so far? Any doubts with this so far? Do you want me to re-explain some part of it? I'd be happy to. I want you to understand this first. I want you to understand this first. Yeah. Is this clear? Any doubts so far? Awesome. Awesome. So, all right. If this is clear, then we can. I'll explain the next problem in the next video. So there's that. So if you haven't, so a few things here. What did we do here? From Stona, you can either jump to I plus 1 or I plus 2, and you have the cost of absolute differences of the heights. And that's what we did. We just did as the question asked. We did it in a recursive fashion, like the backtracking method. We found that was exponential in complexity. So we just stored the answers lazily, and then we returned them as we went on. Then we reduced the complexity to linear, and that passes up a DP probe. All right. Awesome. Awesome. Where's my awesome? So oh, one sec. I think I made a small mistake here. Yeah. Sorry, I just dp of I isn't even present here. Previous equals. Thanks for correcting me over there. Thanks for correcting me with the Biram or already. So this is it. Yeah. Previous to previous equals previous, and previous is equal to min of first jump comes second jump. That's correct. Yeah. Just a small correction there. Awesome. But I hope you all understood this. Got it? All right. So if you haven't subscribed to this already, please do subscribe. And if you haven't liked, if you liked this video and if you found it educational, please do like it. I'll see that as a feedback. Awesome. See you in the next video then. It's gonna happen in like 2 minutes.